let's understand a little bit about the types of compounds that we can get from uh, reactions and some of the way we write formulas. So there's two general types of compounds. We have molecular. So these are going to be held together by what we call covalent bonds. Co together, valent, dealing with the valence electrons. Covalent bonds involve sharing of valence electrons. These are typically going to be between two nonmetals. Ionic bonds, we form ions. So we form a cation and we form an anion. So cations are positively charged, anions are negatively charged. Again, positive, negative, they attract each other. And so these are held together with electrostatic forces. Okay, so what we get with an ionic bond is either a metal and a nonmetal, or a metal and a polyatomic anion. So an anion that's made up of multiple elements. Right, so these are just two views of what these look like. Our ionic compounds, again, we have cations and anions. So what we get with an ionic compound is we get this repeating pattern of cation, anion. Sometimes it's 1-to-1, so something like sodium chloride, that's nice and easy. It's 1-to-1, sodium's +1, chloride's -1, 1-to-1. We get a neutral compound. And that's the thing, is they have to be neutral compounds. And so if we have something where we have like, let's say I did like sodium and oxygen, sodium oxide. Sodium's still a +1, oxide's a -2, so I'd have to have 2 sodiums for every 1 oxide in order to get that neutral compound. Molecular compounds, these are held together through intermolecular forces, so forces that exist between these discrete molecules. So ionic compounds, we get this repeating pattern of positive and negative ions. We do not get discrete compounds. Molecular compounds, we have discrete compounds that are individual things that are held together by these covalent bonds. And then if we have a big sample of those, they're held together with what we call intermolecular forces. When we write our chemical formulas, it's in this sort of a format. So we have our elemental symbol, and then subscripted, we have the number of atoms. So water is H2O. So we write it like this, where we've got the symbol for hydrogen, H, the number of hydrogens, that subscript there, 2, symbol for oxygen, and then if there's no subscript, it's implied 1. So H2O, 2 hydrogens, 1 oxygen. Sometimes I get more complicated formulas like this one. This one is magnesium nitrate, where nitrate, this NO3 minus right here. So this is nitrate. Okay. In the nitrate, we have 3 oxygens and 1 nitrogen. Now, magnesium nitrate, okay, so magnesium is a +2, and this nitrate is a -1, which is why we need 2 of those nitrates for that magnesium, because 2 times -1 gives me -2. -2 plus +2 gives me 0. All right, so we have 1 magnesium, implied subscript, only 1 of those. So we've got this parenthesis, okay? So I have a parenthesis here. So that means the entire quantity of the nitrate has that subscript 2. So I have 2 nitrate groups, okay? So when I look at this, I can actually figure out the number of each individual atom. I have 1 magnesium. When I look at nitrogen, I have 1 nitrogen in each nitrate group, but I have 2 nitrate groups. So what's 1 times 2? I have 2 nitrogens. And then when I look at oxygen, each nitrate group has 3 oxygens, but I have 2 nitrate groups. Well, what's 2 times 3? 6. So I have 6 oxygen. Okay, so that's how we write our formulas. Now, We have this thing called the law of constant composition. So what this means is the composition of a substance is always the same no matter where we get it from. So water is always going to be H2O. It's always going to have 11.3% by mass hydrogen and 88.8% by mass oxygen. Now, the thing is this is by mass. So I'm going to do kind of a rough calculation here, and I'm going to show you where we get the 2 and the 1. So I'm going to take this 11.3, I'm going to divide it by this 1.008. If you look on the periodic table, the mass of hydrogen is 1.008. I'm going to get 11.2. Oxygen, I'm going to do 88.8 divided by 16. Depending on the periodic table you look at, you may see 16, you may see 15.99999. Okay, I'm going to get 5.55. Now I have decimal numbers here. Can I have a fraction of an atom? No, I can't. I can only have whole numbers. So now what I'm going to do is I'm going to divide by the lowest number. So 5.55 divided by 5.55 is 1. 11.2 divided by 5.55 gives me 2. So I have my 2 hydrogens and my 1 oxygen. Okay? So, law of constant composition. Water is always going to be H2O, 11.3% by mass hydrogen, 88.8% by mass oxygen. We always have this law. We also have law of multiple proportions. If I have elements that form different compounds, they have to be, again, whole number relationships between the masses of each of these compounds. Why do they have to be whole numbers? Again, I can't have a fraction of an element. I can do the same sort of thing. If I, instead of percents here, I have grams. So if I take 12 grams of carbon divided by 12, which is the number on the periodic table, I get 1. If I take 16 divided by 16, I get 1. Oh, 1 to 1. 1 carbon, 1 oxygen. Down here, I can do 12 divided by 12. Again, gives me 1. 32 divided by that 16 gives me 2. So, CO2, carbon dioxide. Okay. Throughout your study of chemistry, you're going to see all sorts of different compounds. So this is just some compounds, the different compositions of them. So copper 1 chloride, copper 2 chloride. So you can see that we've got both copper and chlorine. One is CuCl, one CuCl2. And so we have different mass percents of each of those because we have a different amount of each of those. Same thing with methane and octane. We have carbon and hydrogen. So we're going to have different percents of those. I could run that same calculation and get these numbers, CH4 or C8, H18. All right. So all sorts of different compounds and all sorts of different formulas that relate to those compounds.